Okay, let's do a problem together about how to use potential and electric problems to study energy and dynamics of particles that are moving. So here's a classic example of a system that we've seen many times at this point. We're looking at a uniform electric field between two charged plates. And what I want to do is imagine two plates where the potential difference is 12 volts. Okay, so when we get to circuits, you'll see that one of the way we charge plates is we hook them up to batteries, and this is a common battery voltage, which is why you see it in problems like this. Okay, so let's imagine I have a 6.24 microcoulomb charge, positive charge, released from rest at the positive plate, and then it reaches the negative plate with a speed of 3.4 meters per second. And what I want to know is what is the mass of the charge and its final kinetic energy. Okay, now as with all physics problems, there's more than one way to do a problem. And this problem is no different. You should always get the same answer no matter which way you do the problem. Okay, in this case, there are easy ways to do the problem, and there are slightly harder ways to do the problem. And you will find that you just have to do a little bit more algebra or make a little bit more connectivity between parts of the problem depending on how you do it. It does not matter which way you choose to do it. You get the right answer either way, you get the same credit either way, you'll solve the problem either way. The advantage of being able to do it in multiple ways is that you can see how to solve problems depending on what kind of information you're given, but also it provides you a way for checking that you got the right answer depending on whichever way you chose to do it first. Okay, so let me do it what I regard as the easy way first. It may not be the easy way from your perspective. You may have thought to do it the other way because it makes more intuitive sense to you. But I'm going to do this the way that requires the least amount of initial algebra, and then we can talk a little bit about how to set it up in the way that requires just a little bit more algebra, but may feel a little bit more straightforward in terms of physics information that you're more comfortable with at this stage in your career, namely the conservation of energy. Okay, so in this case, let's look at how we set up this problem by simply looking at the potential energy first. Okay, so what I know is that I start near the positive plate and then I go to the negative plate. Okay, and I know that for a particle that travels through a potential difference, I can relate the change in potential energy to the potential difference that that particle experiences as it travels by simply multiplying the size of the charge, whatever it is, times the potential difference that the charge experiences going from one plate to the other. Okay, so in this case, I'm told the charge and I'm told the potential difference. The charge is 6.24 times 10 to the minus 6 coulombs, 6.24 microcoulombs. It's positive, and it travels from the positive plate, from the high potential, to the negative plate, to the low potential. So the change in potential that it experiences going from the high plate to the low plate is positive, and I'm told that that potential difference is 12.0 volts. And so if I multiply those two numbers together, I get 7.49 times 10 to the minus 5 Coulomb volts, but I work in SI units. The Coulomb volt is the same thing as a joule, so this is 7.49 times 10 to the minus 5 joules, which is indeed energy as I expected. Okay, now because I know that when I start at the positive plate at rest, I have no kinetic energy, and I end at the negative plate with only kinetic energy and no potential energy, I know that at the end of the problem, this potential energy that I started with is all going to be kinetic. Okay, so automatically I know that the final kinetic energy is equal to the change in potential energy that I calculated above. Okay, kinetic energy is one of the things I'm asked to calculate. Okay, so I can just say by fiat, because I already computed this, that the amount of kinetic energy is 7.4 times 10 to the minus 5 joules. I'm asked what the mass of the particle is. I know that the kinetic energy is given by a half mv squared, but I'm given the speed of the particle at the time it arrives at the negative plate. So I can solve this for mass. I see that mass is equal to 2 times the kinetic energy divided by the speed of the particle squared. And so if I punch those numbers in, I get that the mass of the particle is 1.3 times 10 to the minus 5 kilograms, which is the other bit of information that I'm asked to solve in the problem. Now, you'll notice what happened here is that I solved for the information in the opposite order that they were asked for. That's something that happens all the time when you solve physics problems, and by this stage in your career, you've probably encountered that fact. But very often we get boxed into trying to solve the problem for part A first, looking for the mass of the particle, and then solving for the thing that we're asked for second, in this case the kinetic energy. That's perfectly fine, but following that approach is, in this case, what I think makes this problem a little more complicated if you start by solving the mass first. So let's just set up how that would have happened so you can see how it goes. Okay, so just as in the first case, we're going to use conservation of energy to solve the problem. And so what we know is that whatever energy I start with in the problem has to equal whatever energy I end with in the problem. Okay, so let me write that explicitly as E final is E initial, which if I break that up into the kinds of energy that we have, this is the potential energy at the end of the problem plus the kinetic energy at the end of the problem is going to be the same as the potential energy at the start of the problem plus the kinetic energy at the start of the problem. And in this case, what I have is I know that at the start of the problem, the particle is at rest. Okay, when it's near the positive plate, that's in the problem statement. So this initial kinetic energy is actually 0. Okay, so if I take the potential energies and I put them together, this gives me that the kinetic energy at the end of the problem is the potential energy that I start with minus the potential energy that I end with. Okay, you'll notice that that looks like the change in potential energy, okay, modulo that it has a sign difference, and this contains the thing that I'm asked to find, which is the mass. So I could write this as a half mv squared, and I can write this as minus delta UE, because it's delta U is the final potential energy minus the initial potential energy, and I have the negative of that. I could solve this for the mass, so this is equal to 2 times minus delta UE divided by the speed squared. Okay, and so you can see how you can start to plug in the things that you're told in the problem in order to get the mass. Whatever that mass is, you can then substitute back into the kinetic energy formula to get the kinetic energy. You'll get exactly the same answer as we got up here, but you have to go through a few more algebraic steps in order to do it. Okay, so I hope that provides you a little guidance. Good luck trying to solve some problems, and we'll do some more problems together sometime.